there was a zoom problem. It quit on me. So I am not going to refilm everything because this can happen again. And I already thought of a specific train of thought to present to you. So I will just continue. So we see that T2 prime minus T1 prime is 0. The arrival events of the two beams to the front and the back of the ship are simultaneous in the frame of the spaceship, but they're not simultaneous in any other frame. So the fact that it is not so implies that the statement T equals T prime is wrong. You see? So this underlying idea of Newtonian physics, universal time of the universe ticking throughout the universe, that time is decoupled from space, that time has a life of its own, space has a life of its own, that time is not affected by reference frames, all that. That assumption is suspect. There's something wrong with that assumption. That's really what relativity of simultaneity is teaching us. And we merely used light as a vehicle to arrive at this idea. It's a natural consequence of this idea that speed of light is the same in all frames, but really it's an effect about it's an effect about time. It's not an effect about light. We can see this further. We already saw a suggestion that time flows at different rates in different frames in the following way, that when we looked at sound, when we sent the sound beams, we saw that delta t front, or since I synchronized the clocks to be t equals t prime equals 0 when the origins pass each other, I can just call it t front, right? No need for deltas. We saw that t front equals L over 2 S minus V, and t back equals L over 2 S plus V. And we saw that this was the value of the times in both frames. Remember, there was a compensation effect. Then in one frame, it's the same distance, but with different speeds. But in another frame, is different distances, but with the same speed. And the two effects compensate each other perfectly. The reason they compensate each other perfectly is because of this form of the Galilean transformation that was involved. In any case, we see that the arrival events take place at different moments in time, and both frames agree on what moment in time it is. Both frames agree that the arrival events of the sound pulses are non-simultaneous. And by the way, what this means is that both frames can make them simultaneous by placing the emitter off center. You can compensate for the fact that it takes longer for the pulse to arrive to the front than to the back by shifting the position of the emitter. And when you shift the position of the emitter, then in the numerator, instead of L over 2 and L over 2, you would have L1 and L2, or D1 and D2. And you can convince yourself that if you shift so that it's L1 to the right and L2 to the left, then again, both frames would agree that the arrival events are simultaneous. So because they both agree on the degree of asimultaneity, by shifting the position of the emitter, they will both agree on the simultaneity. Anyway, there is agreement, but of course there is agreement, because time flows at the same rate in both frames, t equals t prime. So if it takes something 5 seconds in one frame, then observers in another frame would agree that whatever took 5 seconds in one frame also took 5 seconds according to them, right? If we use our contraption of lining space with clocks. If we don't include the time delay due to the signal arriving observer's eyes, right? Anyway, if I eat lunch and it takes me 1 hour to eat lunch, then observers in a high-speed train would also conclude that it takes me 1 hour to eat lunch. Again, if they line their space with rulers and clocks and do all that. It's understood. We never even question that. Well, we never even question that because we assume that time flows at different rates and different frames. But with light, when we went to light, we saw that there isn't an agreement about T front and T back. With light, we saw that it takes L over 2 over C, or I called it L prime. I said that lengths are not the same. We will see why later. And L prime over 2 over C. This is T front. This is T back. So this is spaceship frame. But we saw, let's call it primes, right? But we saw that T front equals L over 2 divided by C minus V, and T back equals L over 2 divided by C plus V. This is the so-called ground. Right. Please understand that there's nothing special about Earth's ground. You might as well use Moon's ground, Mars ground. Ground really means some other frame. So you see, there isn't an agreement. In the spaceship frame, this is really how long it takes for the light to go from the origin or from the center to the front. Observers on the ground say, no, 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 no. This is how long it takes for the light to go from the center to the front. They're describing the same pair of events. Light beam leaving the center, light beam arriving to the front. And again, there's a disagreement about this as well. So that's now the situation where in one frame, you think it takes 1 hour for me to eat lunch. In another frame, you think, no, 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 it takes 1.5 hours for me to eat lunch. You know, these are really pairs of events. You can forget about light beams. Imagine that at those two instances, when the light beam left the center and the light beam arrived to the front, there were 2 explosions. So now remove the light beam and you have explosion in the center and explosion in the right. You time the time difference between those 2 events. And in the spaceship, you say, well, it takes 1 second. And according to the ground, you say, no, it takes 1.5 seconds. The light beam thought experiment was a vehicle to arrive at the idea that timing between a pair of events in one frame is not the same as the timing between the pair of events in another frame. And this is profound, folks. This is profound. What that really means is the following. So I have my space lined with clocks. Okay, and I'm eating lunch. Okay, I'm timing the time that it takes for me to eat lunch. And there's some other frame passing by me. There's a train. There's like this very long train lined with clocks. And while I'm eating lunch, I'm also peeking inside the train and I'm looking at the difference in the clock that passed by me when I started eating lunch and the other clock in the moving train that passed by me when I finished eating lunch. And I'm looking at the difference in those clocks, and I find that the difference in those clocks gives me a number that's different than the difference in my clocks. That's what it really means. What takes 1 second in my frame, what takes 1 second according to clocks in my frame takes different amount of time according to clocks in another frame. And it's intimately tied to the relativity of simultaneity. The relativity of simultaneity brings this idea to the forefront. We will explore this further in the next lecture when we study an effect called time dilation. But we will see that all these effects, relativity of simultaneity, time dilation, and length contraction, they're all tied together. They have to work together. Okay. Sorry about the technical glitch. It's not my fault. I really like my beginning, so I don't want to restart, because every time I restart, something doesn't go right. And it went quite right until the technical glitch. So I guess you'll just have to watch the two pieces. Okay. Well, all right. Thank you.